In this section 1.4, I'm going to be discussing about complex numbers. Now, the first thing that we need to discuss about complex numbers is basically the actual Venn diagram of the number system. Now, this is the general idea of a complex number, so you keep this in mind. A complex number is any number that is either a real number, just like it shows you on this diagram here, or on the outside right here, a non-real number. So, we talked about non-real numbers in section P.3. Now, what is a real number? Well, a real number can be categorized in many different ways. We can start by saying we have two main categories of real numbers, which is the rational numbers and the irrational numbers. We're going to be basically discussing a lot about the rationals. Now, on the irrational numbers is any number that cannot be expressed in the form of a fraction. Now, some examples of irrational numbers that you're going to see throughout this course is the number e, which is called the Euler number. This one has an approximate value of 2.718285, and so on and so on and so on. So this is an approximation for its value. So it is an irrational number because no matter what we do, we will not be able to find a fraction that will actually fit this number exactly with all its digits. So what makes an irrational number? It's a number that has a non-terminating number of decimals. Now, also there's other types of irrationals that we're going to talk about in this course. One of them is a geometry figure, which is pi, which we're not going to discuss here. But then we have square roots, radicals. Now, specifically square roots, that's going to be the main one. But anytime we have the square root of a number that is not a perfect square, that is going to also result in an irrational number. Because if you think about it, like for example, square root of 2, that one is between 1 and 2. Because the square root of 4 is 2 and the square root of 1 is 1. So square root of 2 would be a number between 1 and 2, and it's going to be 1.41 and so on and so on and so on. So it's going to have infinitely many decimals. Okay? Which again, it cannot be turned into a fraction. On the other side, we have the rational numbers. The rational numbers is it talks about all the numbers that can be expressed as fractions. Now we have fractions, regular fractions such as 1/2 or let's say 1/3 and so on and so on and so on. Now we also have decimals that can be turned into fractions, and we know that. So 0.25, for example, can be turned into a fraction, which is equal to 1/4. Then we got let's say 66666, and keep on going. That can be turned into a fraction, that is 2/3, and so on. Now, a decimal is a fraction only when it has a terminating number of decimals or a repeating decimal. So, there's other types of more specific fractions which are called integers. Integers, I'm just going to give you like the best version of it. It is basically a fraction that we can divide into a single number. In other words, -3, it's an integer, -2, -1, 0, 1, 2, 3, all of those are integers because they come from fractions. For example, -12/4 equals -3, so it can be divided into a single value. So that is a rational number that it's also an integer value. Now, more specifically, when we say whole number, that just excludes the negatives. It is basically the same as the integers, but just the non-negative integers, which is from 0, 1, 2, 3, and so on. And then we have the natural numbers, which excludes the zeros. So it's just the positive counting numbers. Okay. So, and on the other side, we have the non-real numbers. What is a non-real number? It is when we have a radical, an even root. Not only the square root, but it's when we have an even root of a negative number. But we're going to be talking specifically about square roots of negative numbers, of course, in this course. Okay. So, now I'm going to give you the definition of a complex number. Now, first of all, we already talked about that we're going to have a non-real solution, or we call it also imaginary solution, where we have the square root of a negative number. So in other words, we're going to call that I. Anytime we have the square root of a -1, we're going to call that I, and I stands for imaginary solution or imaginary number. Okay. Now, if I square both sides of this equation right here, if I square both sides of this equation, what's going to happen right here is this. The square root, this is something for you to keep in mind for future reference. The square root and the square, they are opposite operations. Because remember what the square root means from the previous section? It means the power of 1/2. If I multiply this power of 1/2 times this 2, it's going to give me a 1. In other words, they're going to simplify each other. Okay? So it tells me then that I squared equals to -1. That is the second definition. I need you all to make sure you know this by memory. Okay? Now, any number that can be expressed in the form a plus bi is going to be called a complex number. Now, in the sense that when you have a real number, we don't see the imaginary part on that number. But in reality, we can express it in this form. For example, the real number 1/2, it can be expressed as 1/2 plus 0i. But since it is a 0i, because it is not imaginary, it is a real number. So the imaginary part is non-existent. Now, other types of numbers, such as -3, that's a real number. But if we want to write it in the form a plus bi, that's the same thing as -3 plus 0i, and so on and so on. When are we going to have an I on the number? Is when we have the square root of a negative number. Okay. So once again, the a plus bi is going to be called the standard form of a complex number. Now, let's go ahead and talk about the square roots right here. We're going to do a couple of questions. This problem, we're going to express this in terms of I. Okay. Keep in mind that the square root of 64 means the following. That negative means -1 times 64. And from what we learned on the previous section is that if I have a product inside of the square root, I can separate it as the product of the square roots. So that's the same as the square root of -1 times the square root of 64. But we already talked about right now on the definition that the square root of -1 is going to be called I, and the square root of 64 is going to be 8. Right? Remember, what does it mean by the square root of 64? What number squared equals to 64, which that is going to be an 8. Right? So then an I times 8 is going to equal to 8i. So whenever we have a square root of a negative number, the only thing that negative, basically, so we can skip some of this information, what that negative is going to do is going to turn into an I. And then we get the square root of the number just as we used to. Let's go ahead and discuss the next problem, which is very similar. We're going to simplify this expression using I notation as needed. We got the square root of -216. Now, for this one, it's going to be the same deal. That negative, I'm just going to say that is going to be I times the square root of 216. But now, the square root of 216, that one is not a perfect square. So what we need to do, using the perfect squares, we need to factor it. Using a number that can be divided into 216, that is a perfect square. In other words, we're going to start with 4, 9, 16, 25, 36, 49, 64, 81, 100, and so on and so on and so on. Now, if you think about, there's only a few values right here that can be divided by into the 216. Mainly 4 can be divided into 216, 9 can be divided into 216, but also 36 can be divided into 216. Remember that we're supposed to use the highest possible factor. So in this case, this is what we're going to get. I times the square root of 216, which is going to be broken down into the square root of 36 times whatever gives you 216, which in this case is 6. Then we're going to separate it. So that would be I times the square root of 36. Give me 1 second. Okay, times the square root of 36 times the square root of 6. The square root of 36 is 6, so this is going to give me I times 6 times the square root of 6. If I put all of this together, this is going to be the same as 6i times the square root of 6. and that is this negative square root of negative 216 in simplest form. In other words, in the form a plus bi. But in this case, we see that there is no a. So in reality, it is a 0 plus 6i square root of 6. Okay, but we don't have to put that 0 in the front. Okay. Now let's go ahead and discuss the next idea. Now we're gonna do the basic operations of complex numbers, which is addition, subtraction, multiplication, and division of complex numbers. We're gonna start with addition and subtraction. Now right here, all we're gonna do is we're gonna add those complex numbers by combining like terms. That's what we have to do. So the like terms will be, in this case, we got the 3 plus 7 right here, which is going to give me a 10. And then we also have these two are like terms. Negative 3i plus 4i is going to be positive I, or positive 1i. So this is in the form a plus bi, 10 plus 1i. So all it is required, keep in mind when adding or subtracting complex numbers, is that we need to combine like terms. Now, for the subtraction, there's going to be one small difference, which is that right here, that subtraction sign, that needs to be distributed over the second complex number first. So that's going to give me a 6 plus 4i minus 8 plus 8i. So if I distribute that negative sign, it's going to change the signs of these two. Then we're going to do the same thing, which is we're going to combine the like terms. 6 minus 8 is going to give us a negative 2. Then if I combine 4i plus 8i, that's going to be plus 12i. And this is my solution in the form a plus bi. Now, we're going to get into the products of complex numbers. This is going to be the next idea. Let's go ahead and begin with this multiplication. 4i multiplied times 2 minus 9i. So let's use the distributive property in this problem. So 4i times 2 is going to give us 8i. Then 4i times negative 9i would be negative 36i to the second power, I squared. But then I talked to you about something very important, which is that anytime we see an I squared, that one is going to be replaced with a negative 1 according to the definition. Remember, we talked about that first. I squared is equals to negative 1. So what's going to happen is that I squared, or that negative 1, is going to change that number to a positive 36. Negative 36 times negative 1 is positive 36. All I want you to do now is fix this number because it is not in the correct order. The solution must be in the form a plus bi. This is in the form bi plus a. So let's just switch it over. 36 plus 8i. And now this is my correct way of writing it. Next multiplication we are going to do is this. Find the following product and write the result in the standard form a plus bi. So we are going to do the exact same thing in this problem. We're going to distribute these two complex numbers, and we're going to get negative 5 times 1, it's going to be negative 5. Then negative 5 times I is going to be negative 5i. Then 2i times 1, it's going to be plus 2i. And last is 2i times I, it's going to be positive 2i to the second power. Now, there are two things that we can do here. Number one, we can combine like terms. So negative 5i plus 2i is negative 3i. And there's one more thing that can be done for the I squared right here. The I squared can be replaced with a negative 1. So what is going to happen if I do that? Then that positive 2 is going to change to a negative 2. 2 times negative 1 gives me negative 2. And the last thing we can do is that we can combine like terms. We see that the like terms are going to be negative 5 minus 2, which is negative 7, and we're going to bring the minus 3i down. So this is my solution in the form a plus bi, negative 7 minus 3i. Next problem. Now we're going to multiply these two complex numbers. We're going to do the exact same thing. So we're going to distribute these two. 4 times 4 is going to be a 16. Then we're going to do 4 times negative 7i is minus 28i. Then we are going to multiply 7i times 4 is positive 28i. And the last one is going to be 7i times negative 7i is negative 49i squared. Then when we combine like terms, negative 28i plus 28i is 0i, so we don't need to put that. Okay? So the only thing missing is the minus 49, but remember that the I squared is going to be replaced with a negative 1. So that is going to give us 16 plus 49, and that can be combined into a 65. What is special about this problem? I just want to talk to you about this problem in a little bit. This is something we're going to cover later in a later chapter. These are called complex conjugates. What does it mean by complex conjugates? Two complex numbers that have the same values but with opposite signs in the I. So that's basically what a complex conjugates are. And what's special about them is the following, that anytime two complex conjugates are multiplied times each other, they're going to equal to a real number. Once again, in other words, all of the i's disappear, which means it becomes a real number. Okay, that is one of the special properties of complex numbers, of complex conjugates. Now, let's go ahead and talk about the last case of multiplication. Then we're going to go into the divisions of complex numbers. We got 4 plus 9i squared. Now for this problem, we can do it in two ways. Number one, we can use the formula for a perfect square trinomial. As you can remember, this is in the form of a plus b squared. And the formula for that, if you remember, it was this. We talked about it before in factoring. A squared plus 2 times a times b plus b squared. So the square of the first term plus 2 times the first term times the second plus the square of the second. That's how we read this. Okay, so we can write it like this. So the first term squared plus 2 times the first term, which is 4, times the second term, which is 9i, plus the square of the second term, which is 9i to the second power. So that's going to give us a 16 plus 2 times 4 is 8. 8 times 9 is going to be 72i. And then plus 9i squared is going to be 9i times 9i, which is 81i squared. What is the last thing that can be done here? Well, the last two things. Number one is that the I squared is going to be replaced with a negative 1. So that's going to make that 81 become a negative 81. So it's 16 plus 72i minus 81. And to finalize this, we can combine like terms. 16 minus 81, it's going to give us negative 65. Okay, plus, of course, 72i. So this is in the form a plus bi. This is my solution for that. Okay. Now, we can also do it in a different way. If you wish, you can also do this. 4 plus 9i squared means that you have to multiply 4 plus 9i times 4 plus 9i. You just multiply the same complex number by itself. And then you do the distributive property. 4 times 4 is going to be a 16. Then 4 times 9i, it's going to be plus 36i. Then we got 9i times 4, which is plus another 36i. And finally, 9i times 9i is plus 81i squared. And once again, there's two things that we can do. Number one is that we can combine like terms. 36i plus 36i is 72i. And then the I squared, remember, it replaces with a negative 1. Everything else you see is going to follow the same thing. So 16 plus 72i minus 81. And then we can combine the like terms, which is 16 minus 81, it's going to be negative 65. And then we bring the plus 72i. So a plus bi. And of course, it gives us the exact same thing. Now, we are going to cover the last topic before we go into the last part of the section, which is finding the quotient or the division of two complex numbers. The goal on this division is for us to express the answer in the form a plus bi. In other words, we need to get rid of these 2i from the denominator. One thing that we can do is this. We can divide both of them by the 2, but not by the I. So there's going to be something that we have to do. Remember, the I represents the square root of a negative 1. So it is considered a radical. And when we have a radical on the denominator that cannot be simplified, then we're going to use the process called rationalizing the denominator. Again, to get rid of that I from the denominator. In this case, remember, what do we do when we rationalize the denominator? We multiply it by itself. So I only need to multiply the I because the I is the radical. The 2, it doesn't have a radical, just the I. And you do the same thing to the numerator. So if you look at the denominator, 2i times I, it's going to be 2i squared. But then the I squared, we already said it is equal to negative 1. But then 2 times negative 1 is going to give us a negative 2. Okay? Now, if we multiply the I on the numerator, then I times 10, it's going to be 10i. And then we got the I times negative 9i, which is negative 9i to the second power. And then one more thing is going to happen, which is that the I squared is going to change to a negative 1. So that's going to make it a positive 9. But then we need to switch it over because it must be in the form a plus bi. So let's switch these two. So it's going to be 9 plus 10i. But then that is not in the form a plus bi yet because we have a divided by negative 2. So how can we express this in the form a plus bi? Divide both of them by negative 2. So my final thing is going to be 9 divided by negative 2 plus 10i divided by negative 2. And that is going to give you negative 9 halves. And then 10i divided by negative 2 is minus 5i. Now my solution is in the form a plus bi. Negative 9 halves minus 5i. Next and last, we're going to be simplifying some complex numbers in this form. So let's go ahead and do this problem. This problem says, perform the indicated operations and write the result in standard form. So basically we want to make sure we achieve this in the form a plus bi again. Okay, that's what the standard form means. Now there's a couple of things we have to do. Just like on the previous question, we have to divide the 60 on both of them. But first thing that we have to do, since we have a radical in this problem, is that we have to simplify that radical if possible. Okay, so this is the first thing we're going to do. So it's going to be a negative 12 plus, and then we know that the negative is going to be inside is going to be an I. So what we need to do with the 18, we need to factor it, just like we did before. Okay. So, and to factor it, we're going to use a factor, the largest possible perfect square factor that can be divided into 18. So if we talk about the perfect squares, we have 4, 9, and 16. Those are the ones smaller than 18. So 18 cannot be broken down into 16 times anything, right? But 18 can be broken down by 9, so it would be 9 times 2, right? That equals to 18. So that's the one we can use. So it would be square root of 9 times 2. Then what else did we do? Then we have to separate it. So it would be negative 12 plus I times, right here, the square root of 9 times the square root of 2. Everything over 60. But then the square root of 9 is equal to 3, so it's going to be negative 12 plus I times 3 times the square root of 2 divided by 60. And if we put everything together, then negative 12 plus I times 3 times the square root of 2 is the same as 3I times the square root of 2 over 60. So the last thing we have to do here to write it in the form a plus bi is that we are going to divide both of them by the 60. Negative 12 divided by 60 plus 3I times the square root of 2 divided by 60. Okay? Now 12 cannot be divided by 60, but what we can do is we can reduce 12 and 60 by 12. We can reduce them by 12. And that is going to give us a negative 1 over 5. Negative 1/5. Right? That's what it gives us as a solution. And right here also, the 3 and the 60, they can also be reduced. We can reduce the 3 and the 60 by 3. So that is going to give us a plus 1I, which is just I, square root of 2, over, and 60 divided by 3, it's going to give us a 20. So now my solution, it is in the form A plus B I. A plus B, and here's my I. And this problem concludes section 1.4, which is complex numbers.